Great. Good afternoon, everyone, and welcome to this afternoon session on quantum computing and AI. My name is Unnikrishnan. I'm the Executive Director of the Quantum Center at ETH Zurich. And I'll be your moderator for this panel. So our discussion today is going to focus on two very fascinating and interesting and very different technologies, quantum computing and AI. So of course, we're all very familiar with the impact that AI has had on society, the way we live and work, its opportunities and its challenges. Now, quantum computing is in a much earlier stage of development, but it's often described as our next major leap in computing power. And this is because it's based on almost accurate theory of nature. So how quantum mechanics, which describes how light and matter behave at very small scales. And at these scales, strange new phenomena start to emerge, which you can use to build very new types of technologies. So this is where its power comes from. But this panel, you don't need to understand quantum mechanics. We'll talk about understanding how AI and quantum technologies are different, how they can work together, and what kinds of problems that can help us to solve. So we're going to look at some real examples from fields like cybersecurity, finance, chemistry, physics. And we're going to look at how long it might take before we start to see useful results, and talk about some of the opportunities and the risks that are ahead of us. So we're very lucky to have four fantastic panelists with us today: Grégoire Ribordy, Marina Marinkovic, Steve Suarez, and Nathan Baker. So before we start, I'd like to ask all our panelists to quickly introduce yourselves. Grégoire, let's start with you.
Thank you, Anu. Good afternoon, everyone. So my name is Grégoire Ribordy. I'm a physicist by training, did my PhD at the University of Geneva, and worked on quantum communications. And so today I will talk more about the security aspect of quantum technologies. After my PhD, I started a company called Quantique, and that was quite early. It was in 2001, and as I sometimes say, 15 years too early. It was very lonely at the beginning, but quantum is really happening now. There was a big change around 2015, where a lot of acceleration in applications. And last year, Quantique got acquired by IonQ, which is one of the leading quantum platform companies, computing, networking, and sensing. Bravo.
All right, thanks, Anu. Thanks, Gregor. My name is Marina Marinkovic. I'm an assistant professor for computational physics at ETH in Zurich. My interest is in theoretical particle physics, in particular in strong interaction, how quarks and gluons come together and form protons and neutrons, of which we are all made of. And I'm using quantum computing to find out a little bit more about these interactions in nature, and also co-designing quantum computing experiments together with my experimental colleagues at ETH in Zurich.
Great. Hi, everybody. So Steve Suarez. I used to be at HSBC 20 years. I ran innovation for them, so I'm a recovering banker at this point. I'm CEO of HorizonX. I'm also the co-founder of the Quantum Index. So if you want to know who's leading in quantum computing, you can look at the Quantum Index. I teach. I'm also a teacher. I'm lecturing at MIT on quantum strategy. And I do a lot of board work and advisory work for McKinsey. I'm a senior advisor at McKinsey on quantum computing, Mitsubishi, and a couple of quantum computing companies, which are in the audience now. So if you want to meet some of the CEOs of the companies, doing some really good stuff. And by the way, congratulations on getting the acquired.
Yep. Hi, everybody. My name is Nathan Baker. I lead an engineering team at Microsoft. We're focused on quantum computing, basically building applications that take into account the power of AI and the accuracy of quantum computing, bringing them together. We have a heavy focus on problems in many-body physics, chemistry, things like that. But we cast a pretty broad net and take advantage of the robust ecosystem and developer tools that Microsoft's built in this space. I've been at Microsoft about 3 years. Prior to that, I was at Pacific Northwest National Lab for 12 years. It's a Department of Energy lab in the US, and have a background in chemistry and applied math.
Thanks, everyone. So let's dive right in. I want to start by talking about the difference between what AI is good at versus what quantum computers will be good at. So all of you come from different fields, and we have a very nice spread here from our panelists. So I was wondering if you could all give us an example from your field of a concrete problem where both AI and quantum techniques are used as kind of complementary approaches to attack different parts of a hard problem. So Nathan, maybe we can start with you.
Sure. Well, I'm a chemist, so it's going to be a chemistry example. So one of the things we've been using AI for many years is in the study of chemical systems. And it really serves as a replacement for very expensive classical high-performance computing calculations. So when we apply AI in this space, instead of screening a handful of compounds or a handful of materials, we can screen tens of millions of them. One of the studies we did looked at coming up with new electrolytes for solid-state batteries. And in that case, we were able to look at 32.5 million compounds in 80 hours. If we'd done it using the traditional classical high-performance computing calculations, it would have taken 20 years. So AI has already demonstrated its value there. But you think about the AI models we're using. They're powerful. They allow us to screen things. You can kind of think of it as a big funnel. You put model compounds in the top. They come out the bottom. You hope you have a good one to take to the lab. But they're only as good as their training data, and their training data comes from classical computers. But we know that chemistry problems in material science, you can't solve them exactly using classical computers. The problem gets too big. You run out of compute power. So we make approximations. So our model is limited by the power of classical computing. So one of the things we're so excited about with quantum as quantum computers become more and more capable is the ability to now swap out part of our training data and actually put in the exact answer. Stop cutting corners because of the limitations of classical computing and building in the exact answer that we get from a quantum computer. And our goal there is to, if you think of our process, this AI screening process as a funnel, we will be plugging leaks in the funnel. We'll have more accurate results, sort of first-time right candidates that come out at the end. And that's really the vision and the excitement that we're seeing with quantum computing.
Thanks, Nathan. Maybe Marina, you can go next.
Yeah, actually, my example builds very nicely on what Nathan just said. So in my field, the situation is a little bit different since we've been starting from the standard model of particle physics, describing the interactions of quarks and gluons. And we've been working on this one very difficult problem for the last 40 years. And we've been optimizing classical resources extensively in order to work for that one particular problem. So this is a place where AI hasn't been so successful yet compared to the conventional classical methods, but we've been working on developing AI-based sampling methods in order to increase the input, or to enable the input for learning the properties of the interactions that we are interested in. This is part on the particle physics side, in particular on the theoretical side. On the other hand, in particle physics experiments, this is where machine learning has been making progress over the past 2 decades at LHC, at CERN, in the data analysis of when we have large amount of samples already coming from the particle physics experiments, then this is a situation where we've seen huge advantages already from the AI side. And on the other side, also in lower energies in material science, where we can have large amounts of samples already from, for example, quantum physics experiments. This is where, for analyzing this data, is where we've been seeing that AI has been very successful so far. And where we hope to use quantum is studying phase diagrams of this type of both materials at low energy, so new materials, and also phase diagrams of the interactions of our universe. And this is one of the questions that classical computers currently cannot answer. We need exponentially large amount of resources on the classical side in order to answer these questions. And this is where we hope combining quantum resources, once sufficient resources are available, and AI on analyzing the data which we would get from quantum experiments. We hope that combining the two would answer some of these yet unanswered questions in particle physics.
So it's really some very fundamental questions that you're hoping to answer. So Grégoire, what about you from the cybersecurity perspective?
So we've heard about some applications of quantum computing. One of the applications, actually one of the algorithm, is an algorithm known as Shor algorithm that allows to break the mathematical cryptography that we use to secure our data, and that you actually use all the time. Whenever you connect to a website using HTTPS, there is some mathematical cryptography in the background, public key cryptography, and the security of public key cryptography is based on the fact that certain calculations take too much time to be done on a classical computer, so you can't decrypt information. Shor's algorithm running on a quantum computer can be used to factor large integers, to find the prime factors, and this is a way to break this kind of cryptography, which means that as soon as we have a large enough quantum computer, we will have a problem with the information security as we do it today. We're not there yet, and in a sense, if we think about it, it's interesting that in this particular case, the software, the algorithm was invented before we have the hardware, because if it had been the other way around, it would have been a big problem. We would not have been able to prepare. Now we know about this problem, and we know that we should prepare. Estimates, I was at another panel this morning, there was someone from IBM talking about their quantum program and estimating that this risk will materialize in 2029, according to their roadmap. Is it going to be 2029, 1 year before, after? I think there's still a bit of uncertainty, but what's for sure is that it's coming, and it's coming around the end of the decade. And we need to prepare. How can we prepare? One way is to use quantum against quantum, so to use quantum technologies to communicate and to do optical communications with individual photons, individual quantum particles. And if you do that, you can detect interception, because in quantum, when you measure something, you perturb it. And so that's one way, that's the quantum communication way to secure information in a quantum world. But there is a second approach, which is more the mathematics-based approach. Let's find new algorithms for which there are no known attacks based on a quantum computer. This is known as post-quantum cryptography. And about 10 years ago, NIST in the US, which is the body that standardized cryptography for the US, but in practice also for the rest of the world, launched a competition asking scientists, cryptographers from all around the world, say, do you have a good idea for post-quantum cryptography? Please propose it, we'll test it, and eventually standardize it. And last year, the first set of algorithms was published by NIST as a new set of post-quantum cryptography algorithm. Now, what's important to understand is that with mathematical-based cryptography, you never really have a proof of security. You think it's secure if enough people have tried to crack it without succeeding. But there's no mathematical proof of the security. And where AI becomes interesting is that with AI, there might be new attacks possible, new cryptanalysis techniques. So instead of just trying with the classical way, using classical algorithms, using AI tools to try to attack these new algorithms. And so it's important to bear in mind that the security of these new algorithms is maybe not so well established, will maybe change in the future. And again, if we look at NIST, as soon as they finished the first competition, they immediately started a new one to find another bunch of algorithms in order to have a kind of a backup solution in case there's a problem.
Thanks, Grégoire. And we'll talk a bit more about the risks and how to prepare a bit later. But Steve, what about you? So you worked in finance for a while. So what would you say, where is AI and quantum used in finance applications?
Yeah, I do want to piggyback off of what Grégoire talked about the 2029 date, because I think we got a more immediate problem on harvest now, decrypt later. So maybe when you give that update, you can kind of talk about that.
I will think it.
We want people to act now.
Yeah, of course.
Bankers like to make money. So they want to say, how can I use quantum to make money, or they don't want to lose money. So one of the things that we've done is use quantum and AI to do fraud detection and fraud anomaly. When you guys are here traveling and your credit cards get denied, it's because they overprotect. They want to make sure that you are who you are. And so there's algorithms out there that Quantum can actually help detect based on all kinds of information. We have to dumb down some of these models because there's so much data out there that we can't use all that data to make it. So imagine if I can use your phone, I can use your geolocation, and know where you are, and where a transaction is. So if you're here at Davos, and there's somebody using your card in Thailand, then you know that there's something going on because we're using all of this data and working through that. We're also looking at collateral optimization, pricing optimization, derivative pricing, fraud at risk. We can do stress tests and that kind of work. So it's incredibly powerful. So if I can manage fraud better than my competitors, it means I can make more money.
Great, thanks. So let's dive a bit more into some of these applications. So first, I want to ask Marina and Nathan. So you both talked about these kinds of big questions that people are using quantum and AI as kind of tools in their toolbox to investigate. So, and this is really like simulating complex systems is really what quantum computers were initially envisioned to do. So why is this so hard? Can you talk a bit about the bottlenecks and when you think we'll start to see useful results using these techniques?
All right, so I started a little bit about why is it so hard to, on the AI side, to beat some of the already known classical algorithms. I'm confident that this will happen in the future, but it takes a while because, as I said, we've spent 40 years optimizing and fine-tuning for conventional algorithms for classical computers. On the quantum side, one of the main obstacles is that the machines that we are working with currently are not, the majority of the machines are not noise-free. So we need to work similarly as in the beginning of classical computing with relatively naive algorithms. We have to deal with the experimental uncertainties already in our computation. And this is something we don't worry about when we work with zeros and ones with our classical computers, with classical bits. There is also potential for mistake there in this calculation, but this potential for error has been exponentially suppressed over the past many decades of development of classical computers. So I think we need fast development on the hardware side and on the algorithm side in order to control for these potential errors. And despite the case that our current situation that our quantum hardware is not perfect, there are still many interesting applications, and we are on the verge of pushing beyond what classical computers can do at the moment, as Nathan already mentioned.
Your answer was very similar to what I was going to say. I think there's two things we need. We need better physical qubits, and we need better logical qubits. And they go hand in hand. So the physical qubit that, for I don't know how many quantum aficionados we have in the crowd, but a physical qubit is the quantum counterpart of the transistor, right? It is the information processing unit. But as Maria said, they're noisy. They forget what you tell them. They decohere, they lose their quantumness. The way you fix that in a quantum realm is you use error correction, but you use a special type of error correction. You combine multiple physical qubits together so that together they are more robust, and that forms what's called a logical qubit. Physical qubits have to hit a certain threshold before a small number of them can make a logical qubit. And so we need the physical qubits to get better. We need their operations to become more reliable. And then we need better ways to put them together with error correcting codes into logical qubits. At the end, what we want is a collection of well-behaved physical qubits that will do reliable operations. And that means we need to have logical qubits that will detect errors, correct errors, and carry on with the computation. All three of those things are important. But the pace of progress has been really remarkable, right? If you rewind to even maybe a year and a half ago, people were looking at maybe one logical qubit, but it only did one of those three things. They said, uh-oh, there's an error. Or it would say there's an error and I can correct it, but I can't carry on with the computation. Since then, we've seen over a span of just a few months, 4 logical qubits, then 20 logical qubits, then 28 logical qubits. We're working with Denmark, with the Novo Nordisk Foundation and the Danish Import-Export Fund to deliver a system that has 50 logical qubits. So the pace of progress is remarkable. But I also liked the start of your answer about the very, very healthy competition between AI and quantum in this space. If we think about the goals of science and how science helps humanity, I don't actually care who wins, whether it's quantum or whether it's AI, because every time quantum pushes the field forward a little bit, someone comes along with an innovative AI approach and either catches up or surpasses. And if you think about it from a society standpoint, from a science standpoint, that's fantastic. We need to keep pushing forward on the quantum side, challenge the AI folks, give them a run for their money. They will catch up, and you will just see progress in the whole field if you have those two things working together.
Can I add to that? Because I think to Nate's point, everybody talks about quantum advantage. And that's when quantum can do it better than classical. But exactly what happens is, as we develop these quantum algorithms, and I've seen it in, I've seen quantum guys write algorithms that were fantastic, and then the classical guys go, oh, I see how you've done that. They sharpen their pencils and make that better. So even quantum advantage is changing. So every time quantum gets better, classical computers get better. So it is changing. Eventually, we'll have the qubits, and I do know a company that has 80 logical qubits in the US. And once it gets that, then there will be very specific areas that, without a doubt, will have quantum advantage. So it's exciting times, actually. But they're always going to be working together. It's going to be a hybrid approach. It can't just be quantum versus classical, because I could tell you without classical, we won't have quantum computers that are going to, because all the working and getting the information in and out, you'll need a classical computer to do that.
That's actually often, if I may add, a misconception. The fact that quantum computers are not going to replace everything. You're probably not going to have a quantum laptop anytime soon. But in data centers, you have CPUs, GPUs, and QPUs, and each of them will be good at certain part of the problems.
Yeah, and this is already happening in Europe in several computing centers. On top of classical CPUs and GPUs nowadays, which are mainly used for the AI computations, several centers have ordered or already operating quantum computers as well for scientific research.
And I think probably you all get asked a lot, like, when will we have quantum computers? And people are always looking for, like, in this X number of years. And we often say that's not really the right question to ask, because it's more, we have to start preparing now, and we have to start educating people on how to use these tools. So on that topic, and on the topic of risk, so we're talking about these technologies that really transformative and could give us huge amounts of computing power that we haven't had before. And we're now seeing from AI some of the consequences of this. So people are learning about lessons that we've learned from the AI revolution in terms of governance, deployment, misuse, etc. That we're in a position now where we can already kind of start thinking about this for quantum computing and quantum technologies more broadly. So Steve and Grégoire, you've had both had a lot of experience in preparing businesses for these kinds of transformations, and from different perspectives. So Steve, you worked in consulting and executive education, and also in convincing companies to invest in these kinds of radically new technologies. And Grégoire, you were one of the founders of one of the world's first quantum companies when this was still quite an academic field. So I'm curious what you both think about how would you advise people to prepare for the quantum, revolution, and what lessons do you think we should learn from AI?
I love analogies, so I'll kind of use the analogy as the quantum is like a marathon. You don't show up the day of marathon and just expect that you're going to run and perform. It's about doing the education, all the preparedness. I think the thing with AI, everybody in this room has access to AI. You guys can all use the technology. Once quantum comes out, not everybody in this room is going to have access to it. Not every company is going to have access to it. And the companies that act early, that educate their staff, that get access to these systems, that get access to the talent, will have such a great advantage over the companies that don't, that I'm really betting on that the companies that get early and use this technology are really going to separate themselves from the other companies. So the risk is doing nothing, or what I run a strategy company, so waiting is not a strategy. The risk for the companies that don't do anything, they say, let me wait to see as it gets better. The risk is you're going to get left behind. The risk for humanity is that it'll create a digital divide. So the countries, the nation states that are using this technology and the ones that don't, that worries me, because I think there's going to be some countries that are going to get way ahead of other people. We're seeing some of that kind of in AI, right? In some of the countries we are. And I live in Dubai, so the UAE actually gave all of its citizens access to OpenAI and everybody for free. Getting access. Quantum, they're not going to be as nice to say, hey, you guys can all get access to quantum computing. So the strategy I give to companies and the stuff that I do kind of with the quantum index is I work with the companies to make sure that they understand what they should do now. And there are waves, and there are things you should be doing now, especially in Grégoire's world, as far as protecting yourself. Quantum is more than just compute. There's sensing and communication. Again, going back to education, make sure you understand that piece, understand how to use it, get some muscle memory, and then do experiments. Experimentation is the best way to learn.
Yep, and so if I add to this in the security field, you must start preparing, and you must start now. Steve mentioned the harvest now, decrypt later kind of attack. You have to see that with cybersecurity, there are typically two things that you want to achieve. Guarantee the confidentiality of some information and the integrity of this information. That it has not been changed when it was transferred. This is achieved with mathematical cryptography. With confidentiality, you have a risk of information being intercepted today in encrypted format. The adversary may not have a quantum computer yet, but the information is stored, and as soon as a quantum computer becomes available, the information can be decrypted and used for bad purposes. Of course, so it depends on the kind of information. If it's a credit card number, or maybe that's not so critical. But if it's medical data, genetic information, strategic information, national security information, that's critical. And the time span that you want to protect the information can be quite long, 5, 10 years. And so it means that you must use some technology that remains secure for the time span of the information. And so if you're exchanging some information today with a process that is not quantum safe, and a quantum computer becomes available in 2029, it means that all of this information becomes vulnerable. And even if you start now upgrading, you're retroactively vulnerable for the past. That's important. That touches confidentiality. Integrity is a bit easier, because for the digital signatures and this kind of applications, in a sense, you can re-sign just the day before there's a quantum computer. So blockchains, could be re-signed just before, let's say on January 1st, 2029, and you're still good. You have to make sure you're capable of doing it. You have the resources, but you can wait a bit longer. So anyway, it's very important to have a strategy to migrate your security to quantum safe security. And for certain systems, it will be super easy. If you use Google tools, Microsoft tools, Office 365 will be quantum safe. You don't have to worry, that will come for free. For certain systems, special system, ERPs, special banking systems that you've been developing for years, some parts still written in COBOL or things like this, it will not be possible to easily retrofit and upgrade them to quantum safe, or it will take a lot of time. And think about OT and IoT, where security is pretty shaky. That's also very important. So if we look at the past, there's been some cryptographic migrations already. Without going into too much detail, there was a standard algorithm called DES, which was standardized in the 90s, and then was removed at the beginning of the century, upgraded to AES, a new algorithm. If you look at the time it took from the date where the regulatory body said stop using it to a point where all the banks, all the ATMs didn't have these anymore, it's more than 10 years. And so in a sense, as a society, we're probably already too late to complete this migration in a seamless way.
And that's why I said that you said 2029 or and I was just saying, guys, so don't think you can wait till 2029.
So in general, if you deploy some IT tools today, you need to ask the question, is it quantum safe or not? And then also start looking at what you have already deployed, what's critical, where do you have long-lived data, and start upgrading this.
And do you find when you try and talk to companies about this, so one thing that we always hear is quantum is so complicated. How do we actually, do this ourselves, and what's going on, and what's the status of hardware? So generally, there's this aura of it's a very complicated, mysterious technology. So how do you kind of reckon with this, and when you talk to companies about how we need to start preparing now?
I think. Well, first of all, there are some regulators that come up and say you should stop using these tools by this date. You should be ready. So very often security is compliance driven, and so if it's compliance driven, you read the rules. You just have to ask yourself, how much time do I need to be compliant? That's a key question that Steve was saying. But in general, I think that the idea that quantum is a complex topic, so people cannot really adopt it, I don't believe that's really relevant, because if you think we use smartphones, they're based on classical electrodynamics. Who understands classical electrodynamics and Maxwell equations in this room? Probably not a lot of people. You still love using this technology, and I think with quantum, we're still in this early phase, a bit immature magic phase, but eventually it'll become mainstream, and you will just use it without worrying about it.
Yeah. Maybe connecting a bit on both what Steve and Grégoire said, I think one of the keys for the future is also having enough quantum-educated people to implement these changes or to devise strategies. So quantum education and what goes by the name quantum workforce is going to be one of the challenges in the future once we have this technology, people who will be working on producing it, on implementing it, on writing algorithms for that. So one of the next sessions here, I think in the room or in the house definitely is going to be connected to middle school education, and I think we should start thinking about also bringing the understanding of quantum earlier than what's currently done at the universities, and many countries are already doing that. There are also national initiatives in the US, in Europe as well, to bring quantum earlier to the kids so that they would have a chance to potentially have better intuition for quantum once it's there.
And I'd like to add to what Marina said and what Steve said, it needs to be global as well. It can't just be education focused in the countries that are almost destined to get quantum. When we build out teams in quantum computing, the most effective teams have talent from everywhere, right? Our organization has people from all continents. And we are starved for talent in this field. And it's only going to get worse as quantum computers get more powerful and more people want to use them. So I can't emphasize enough Marina's point that we need to be thinking about workforce. That is one of the limiting factors. I probably should have said physical qubits, logical qubits, and workforce. And it needs to be global, because good ideas don't just come from one place in the world. They come from everywhere. And we need to be deliberate about how we train people.
And if I may add a point with quantum, one of the challenges with the workforce is that it's very multidisciplinary. You need quantum engineers, and typically people are either physicists trained in quantum or electronic or computer engineers. And that's a challenge. So over the years, what we've had to do is hire engineers and train them in quantum, or take physicists, but that's not the best approach. And there are now more and more programs. I think ETH, for example, has one such program in quantum engineering, which is very important for the field.
Yeah, I can't help. I'm going to warn you. I'm putting a plug from quantum education to the people in this room. At MIT, we have 5 classes on quantum computing and quantum for executives and stuff. So there is good information. My suggestion is go out there. You don't have to do it with me, but there are other classes out there. But I think I'd like to say we're the best, but anyway.
We also have one at ETH now.
Yeah.
Like in 4 days, you can learn some basics, and it's great. I think there's so many more of these educational opportunities, and as we get more and more brilliant people coming into the field, the pace of progress also accelerates, and we attract more and more people from engineering and from chemistry to look at applications, and so that's another factor why it's so hard to predict when will we start seeing very useful results. So I have one final question before we go to questions from the audience. So there's a lot of miscommunication and hype, as we touched on, around these two topics, and in particular in combining quantum and AI. And we've heard today from our experts some real problems where they see real potential, and that also the fact that we should be patient and how we should educate more people to get involved. So I'm wondering from all of you, what's the one misconception that you'd like to clear up? Is there anything that you hear a lot from people that you want to set the record straight for the audience in this room? You want to go first, Nathan?
I think it was said already. Quantum computing is an accelerator. And so the notion that quantum computers will solve all problems is a misconception. Quantum computers will solve very specific problems in the same way you deploy a GPU very specifically for certain computational workloads. What's exciting is GPUs started out, the G in their name was for graphics, and they started out solving graphics problems. And then someone said, wow, they're pretty good at linear algebra. Maybe I should do that. Then someone said, well, you know, my AI problem kind of looks like linear algebra, and you watch it grow. And I think you're going to see the same type of progress with quantum computing. Right now we say, look how good it is at chemistry. I'm so excited, and particle physics. But the field is changing so quickly, just like you said, it's going to build on each other. And in the same way the GPU started out its life thinking about graphics, you know, quantum computing will start its life thinking about many-body physics, but I think it'll grow. But it will still be a special purpose device, and they will work in an ecosystem. You'll have HPC and GPUs solving AI problems. You'll have quantum generating data to make those AI problems more resilient first time right, and they'll work together in an ecosystem.
I think from my end is you don't have to be a quantum physicist to get into quantum. It's a great opportunity to get into this field, learn about it, and get engaged. To Grégoire's point, this is going to be the greatest upgrade in human history of cryptography. It's not, will it happen? You have to do it. So think about the 20 billion devices that the World Economic Forum is talking about. They all, if they want to be protected, have to upgrade their cryptography. So I'm a business guy. Think about that from a business perspective. Think about we have to upgrade security. We have to be crypto agility. In other words, we're going to get new algorithms. So how are we going to shift those algorithms? And we need people to help these companies. And right now, there's not enough people to do it. There's not enough companies. So if you want to position yourself well, this is kind of the place where you need to position yourself, because from a business opportunity, one of my other hats, I'll put on my McKinsey hat. I'm a senior advisor at McKinsey, and we have a quantum report. We're going to launch the new one here in April. Take a look at those numbers and look at the future between now and the next 10 years, how much money will be in this and how much opportunity that's going to create for the people that get involved in this.
Right. I agree with Steve that you don't have to be a quantum physicist to work on quantum, but you can also become a little bit of a physicist when you start working on that. So I see this a little bit as an opportunity as well, maybe romanticizing a little bit theoretical physics, but I think it's really exciting that, exactly as Grégoire mentioned, that we have so many transistors currently on our device that one day we might be having access, maybe if not carrying them around, but definitely on cloud access to these very exciting physics experiments which are enhancing our power to solve dedicated problems. I find this super exciting. And I also build on what Nathan already said. So there is this healthy competition between AI and quantum, but I think that the future will be the two of them working together. So keyword would be hybrid computing, where we will have classical computing units or graphical units working on the AI problems, and we can also, already nowadays, we are using AI in order to tune these quantum experiments and to reduce noise in quantum experiments. So there is a huge possibility or opportunity in synergy of these two technologies, as the name of this panel says.
And then maybe from my perspective, since I don't come directly from the field of quantum computing, I'd like to say that quantum technologies is much more than quantum computing. We've talked about computing, but once you start building computers, you'll want to network them. And so there will be quantum networks. If you want to keep the quantumness, when you network computers, you cannot do it with classical networks. You need to also send quantum signal. So that's going to be an interesting field. There's the field of security that we've already discussed quite a bit with Steve. One example, there's already a mass application of quantum technologies in the field of security. One of the things quantum is good at is generating randomness, good random numbers. This is useful, this is important in cryptography for keys. And at IDQ, that's one of the topic we've worked on. And here I have you won't see it because it's small, but that's the point. A tiny chip, 2 by 2 millimeters, which is a quantum random number generator. So it's actually a quantum chip. It does something very simple. It just tosses a coin, essentially, but with a quantum coin, so that you're sure that you get 0 and 1 completely randomly. But this is used in applications such as smartphones. There are Samsung smartphones that use this chip in order to guarantee good randomness for whatever application they are. So security, and then maybe the last application of quantum is sensing. Since with quantum you work with these elementary objects that are very sensitive, they're excellent to sense physical properties. And so there are ways to measure the magnetic field, gravitational field, et cetera, et cetera. And so that's also a very interesting topic where also probably there will be very soon, or there are already some applications, but they're not as grandiose as quantum computing, so you may not hear about them, but that's also a field to follow.
There are many exciting potential applications of quantum technologies in general. So now we've got some time for questions from the audience. So we should have some mics going around. So if you just raise your hand if you have a question. This one in the back. Oh, this one there, yes. Go for it.
It's kind of warm, is it?
Yep.
Yeah. Hi, everyone. Thank you so much for the panel. Alona Logvanova, I'm the Chief AI Officer at HSF Kramer. My question is around the near-term effect, essentially. So how soon do you think quantum will become available in more of an organizational sense, right? I really take the point that Steve made around organizational readiness, right? And the organizations who get there first will have a significant advantage. I completely agree. I'm wondering whether you think that's 18 months away, right? 3 years away, 5 years away, realistically.
Can I take that first?
Sure.
Listen, the world around us is quantum mechanical. We just got to be smart enough to get that technology. There are quantum computers out there. They're just the early stages of it. And so it really depends on the use case and what you're looking, but the quantum computers are out there, and every week, and Nate could probably, I know these guys have been doing a lot of really great stuff at Microsoft, but every week there are amazing advancements in quantum. So as far as giving you a date, it really depends specifically on what you're looking for and how do you apply. But this is going to continue. It's like the classical computers. It didn't go from where they were to like a Pentium or the supercomputer. Along the way, there was a lot of advancements, and every time it got better, we were using it. Like in the 60s, we were using it to kind of compute to help go to space. And so quantum computers are there today. They're just not as strong, but they're getting stronger. So the smart people are finding ways on how do I use the computer that's there today to start getting some advantage. And I think we were talking about algorithms and Shor's algorithm that was developed way before the actual hardware was. It's developing these algorithms, and there's a quantum company in here that does exactly that. Sumit, you want to stand up and just, that does exactly that in quantum computers, is developing the algorithms. Once you develop the algorithms, once that computer gets strong enough, that algorithm has a quadratic or even an exponential value. So that's why I tell people start working on it now, start solving the problems now, because the work you're doing is actually going to have a speed up once the hardware catches up.
And maybe just to add to that, just to make sure, emphasizing Grégoire's point, because these could really break cryptography today, that we should really start thinking about it now. So we shouldn't be looking at a future date. We should start preparing right now for this. All right, we had another question. I think it was over there. Yes.
Hi, my name is Vinicius. I am from the Brazilian federal government. My question is, how quantum might impact large language models training and inference?
So I think one of the first things quantum will impact is a related set of models, right? There's many different families of AI models. And we've seen a lot of exciting work coming out of graph-based AI models. They get used to sort of simulate the basic behaviors of atoms and molecules and materials. And that's a case where we see a one-to-one mapping with the type of data that would come out of a quantum computer and the type of input needed to train these models and the types of predictions that they'll make. I think that'll probably be a nearer-term benefit that we'll see with quantum and AI coming together. But, you know, large language models tokenize all sorts of interesting things. They can train on all sorts of interesting data sets. So I would never discount the ingenuity of folks who can take advantage of a new data set and use it to improve a model.
Hi, I don't know if you see me. First of all, thank you, super interesting. Name's William. Do you think that quantum could be the next nuclear in some sense? Because, you know, you're talking about preparing yourselves, like institutions and companies should prepare. Do you think that countries should also look into it, governments should get involved?
Governments are getting involved. They're trying to invest, but yeah, I would let somebody else governments are actually trying to get involved and trying to invest themselves in some of the companies. I don't know.
There are large quantum initiatives in almost every country, even Switzerland, which is typically not very initiative-driven, more bottom-up, has a quantum initiative. But the EU has a large initiative. In the US, there's a quantum bill. And so there's a lot of investment. You know, what you have to see is that one way to look at quantum, it's going to be a revolution and the birth of a new industry. And so if you are a government, you want to capture some of this value creation by having some local, some activities locally. And there's also now more and more the aspect of sovereignty, technological sovereignty. Yeah. I must say, having been in quantum for a long time, I've seen it as being a completely open field where, you know, at conferences, people from China, the US, Europe, where scientists were talking together. Now, you know, there are conferences where people from certain regions are not allowed to come anymore. There are export controls in place. For me, it's also a bit of a concern, this approach to technological sovereignty, because I fear that it will slow down the progress and the adoption of quantum technologies.
And you've got areas competing to try to attract people. I mean, I know we've got somebody from Montana here that's trying to bring quantum to Montana. You've got Quantum Basel right here, the person who runs Quantum Basel, and trying to bring it to certain sections. So it's interesting because now everybody sees the value, and they're trying to attract the talent and attract the people to their region, their countries. So it's exciting times. It's an exciting time to be in this industry.
It's challenging also, this technological sovereignty, because EU wants to buy EU technology, US technology, and you know, I don't know if we're Chatham rules here, but my perspective, I would say, probably not. I would say, so don't repeat what I say, but I would say today, you know, we're still in the early days, and so quantum is not super useful yet. So it's going to be very useful, but it's not yet very useful. And so if you're a government procurement agency, you're going to say, I'm going to buy my local, supplier. If I'm French, I'm going to buy French technology. You don't look at the performance of the products. You just take local because you also see the aspects of developing a local ecosystem, training people, etc. But very soon, when quantum computing will deliver real competitive advantage, if you are a French bank, you don't care if the French, if there's a French quantum computer, you'll buy the best quantum computer available to derive value out of it. And so this transition has not started yet, but will happen very soon, I think.
All right, question here in the front.
So thank you for the really interesting panel. My name is Laura Kiviharju, and my background is AI and cybersecurity governance. And I would like to ask, what would be your message to startups and scale-ups? So not necessarily like quantum scale-ups, but maybe they are in fintech, in health tech. Like, what would be your message and advice? First of all, from do these smaller companies, will have access to quantum capabilities? And then from the security point of view, so these are companies developing now new products to be used in maybe big companies with sensitive data. Can they then implement these quantum safe standards or algorithms today?
Yeah, so from a security point of view, yes, these standards are as they should be, publicly available. There are open source libraries for some of these algorithms. So I would say it would be a mistake not to adopt them. It's not even a question, I think. From a question of accessing quantum computing resources, for example, for small companies, there are initiatives. I guess Quantum Basel in Switzerland is one example where there's an organization that has quantum computing power and makes it available to various users based on projects that they want to run. There are also got some initiative to allow countries from the global south also to bring use cases that may not be obvious for maybe traditional researchers. They can come with use cases and try to solve them using quantum computing. Hosted by CERN in Geneva, there is the Open Quantum Institute, and I'm sure there are other such initiatives around the world. So I think it's important. That's maybe a call to the quantum companies is to make sure that they support these kind of initiatives to make these resources available, maybe not purely for profit, but also in a way that users that are not cannot pay everything. And I think it's important because probably some very good innovation will come out of this.
Yeah, maybe a concrete example related to AI and quantum. So, for example, Swiss AI Initiative has recently grouped together industries, especially small startups, but also larger companies, together with academia, and access to Swiss Supercomputing Center was made possible for joint academia and industry partnerships and projects. So something similar for AI is something that we could also envisage in the future. And many of existing, albeit small, quantum computers are already available through different cloud services, so paid access is already possible. So it's the right time to jump on the train.
And another thing to add is a lot of people are now hosting quantum hackathons where even students can kind of play around with these different quantum resources. And I think this is a very nice way to get kind of early education going, and they have some problem, they work on it on a weekend, they have access to current quantum hardware. Yeah. All right, do we have any more questions? I think we have time for maybe one final question. Have one at the back over there.
Hello, thank you for a great panel. I guess we had a few questions about the technological aspects and the future aspects, but what about financial perspective? How much are companies spending on this at the moment, and what do you think that they're able to dedicate in their budgets currently and perhaps even in the future, just to get an understanding of how big it's becoming?
Yeah, if you want to, there's a website called the Quantum Index, and you could look by industry, and you could see who's writing the most research papers, patents, who's got the largest teams, what are they using them for? And it's very interesting. I mean, actually, business-wise or government-wise, Germany isn't really putting a lot in trying to build stuff, but their industry is using a lot. So think of Volkswagen, BMW. E.ON actually is doing amazing work using quantum computing. So that's kind of a resource that you can use to see what are actually, because that's where the money comes in. It's not so much you got these big companies making computers and getting billion-dollar valuations, which is happening, but you got to look at the industries and what they're using to do drug discovery, because I think this is where it's going to happen first. It's kind of in what these two were talking about, banking, energy, life sciences. where the opportunities go. So there's a lot of companies actually really engaging in this and doing some pretty cool stuff.
All right, then I think that brings us to the end of the panel. So I want to thank my panelists for a great discussion. Thank you.
Thank you.